Okay, so yesterday I gave a brief introduction to these different aspects of materials that are used in electronic materials. So particularly when we discuss or talk about things like how transistors or diodes, uh, what are the materials that are used. So before going into that, those particular materials that are, these are like semiconductors. So let's look at the classification of materials. And so I told that so one type of classification is based on the structure. So let's start with that. So let's look at the crystalline material. So what is a crystalline material? So let's use this. So if you take any solid state material, so you will it consists of large number of atoms, and these atoms are arranged in a particular manner. So they have a regular arrangement. So it's a regular periodic arrangement, and these periodic arrangement, it's like a geometric arrangement, and it happens in a three-dimensional space. So like to give you one example, so let's look at just one dimension. So what you have is in one dimension, so you can have atoms which are arranged in such a way. This is a one-dimensional arrangement of atoms, and this is a long-range order with periodicity A. So this is a one-dimensional periodic arrangement. So similarly, you can extend it to the two dimensions as well. So if I put or put atoms in this manner, so in two dimension, so I will get a periodic long range order crystal in two dimension. So itself, when you look at this, so again, one can have a periodicity A along this and another periodicity. So it may be, let's say, B along the y-axis, let's say. So, or it can be same or it can be different. So this long-range periodic arrangement, in fact, can be represented by a very small unit known as a unit cell. And what is this unit cell? So unit cell is nothing but, so let's say look at, if I take this as a small unit, and now I repeat it along this direction and along x direction, let's say. So if I repeat this unit in both directions, so I can obtain the crystal, or I can create the crystal by repeating this unit. And this unit is known as a unit cell. So in two dimensions, so let's say this is so if I extend or put this unit cell repeated times along the x as well as along the y axis, So I can create the crystal, and basically this unit cell represents the crystal itself. So this concept you can also extend to 3 dimension as well. So now in case of this so in 3D, so for example, so if I extend this arrangement in 3 dimension, so on the left hand side, what you see is arrangement of atoms, and this is extended over both x, y, and z direction. And again, it has certain periodicity in all 3 directions, and you can represent or take a small representative of it, which is shown here on the right hand side. So this here, so this is your unit cell, and if you repeat it in 3 dimensions, so now not only in x and y but along in the z axis, for example, so in all 3 directions, if you extend it, so you can create the crystal, and this is the smallest unit cell you have. So there is a way to so here you see a name, something known as a lattice I have written. So what this lattice means, it is actually a mathematical representation of the crystal. So lattice is nothing but, what is a lattice? So lattice is a mathematical representation of the crystal. And basically what you it means, a lattice means it's a infinite arrangement of points, so just simple points in space. So since we are talking about a 3 dimensional space, so let us say it's in a 3 dimensional space, the arrangement of points with certain which follow certain periodicity. So that is your lattice. So that is purely a mathematical concept which is being used in crystal to represent the crystal in a mathematical term. So that's why you will hear a lot about that when we talk about crystals. So instead of talking about crystal structure, we say, so what is the lattice? What is the lattice structure? So that means what is the so the points, how they can be arranged in a regular manner in 3D space. There can be particular ways they can be arranged. So for example, here what you see is it's like a cubic ordering that you see clearly. So you have a cube which you take, I mean, all the points that you have are basically can be represented by a cube. So it has a symmetry which is cubic in nature. So this lattice, when we talk about the lattice and we talk, the mathematical representation is normally we say any point on the lattice should be represented by a lattice vector or a translation vector. So let's call it T, and this can be represented by this component form. So let's say MANB plus into C. So something like this, where M, N, and P will be integers, and A, B, and C are the unit cell vectors. So here, when you look at this cube here, so we can define here, let's say this is A, this is, let's say, so this dotted line, what you see here, this axis, so let's say call it, so this is B, and this one is C. So this is the smallest, the vector that you require to define the unit cell. So A, B, and C will define the unit cell, and then if you want to go from one lattice point to another lattice point, so you need to do a translation operation. So you have to translate it in the 3D space. And how do you do that? You can translate from one point to another point using this equation or this expression. And for a lattice, it is required that this m, n, and p has to be integers. So then you can create this lattice infinite arrangement of points in 3D space, and which also resembles a lot to crystals. So in fact, in crystals, so when we talk about a crystal, we say crystal is actually consists of lattice. So that means this arrangement of points with which follows one of this translation, plus then you need to put or add atoms or molecules to those points. Okay, so just taking points, it is just a mathematical representation. So there is no physical meaning to it. So crystal will have a physical meaning only when it is associated with some atoms or molecules, and that is what is normally called as a basis. So basis is nothing but it can be one atom, or it can be more than one atom. So it can be 2, 3 atoms which are associated with one lattice point, or it can be a molecule. Okay, so anything is that is you associate with a lattice point, so that will be we will call it basis. And then when you put these two together, so you will get crystal. So lattice is only a mathematical arrangement of points with certain periodicity. So example is like, let's say, cubic. Okay, so this is just a lattice. When you associate these lattice points with some atoms or some molecules, so then only you will get a crystal. Okay, so yeah, here, okay, I'll give a few examples, and then we will see some later on some more examples of this structure, so that it will be much clearer to you. So if you have any question in between, just you can ask or let me know, okay? Or you can type in the message box, so I will try to answer that. So, so when we look at, let's say, this 3D arrangement of points or the lattice, and then so there can be many representations. So we will not discuss all the different possibilities. So typically there are 14 distinct ways you can form a lattice. So these are called a Bravais lattice. But we will take a few of the examples which we will encounter for different materials during this course. So one example here is, so I have already plotted here. So this is, again, this is a cubic lattice, what we are talking about here. And what you see, there are 3 different possibilities. We can have a arrangement of these lattice points, which will lead to a long range order. So you can probably, like if you can put points in space in a random way, so you can pack as many as points. But when we talk about they should follow certain uh, translation, so they should be periodic in nature. So you can only do it in specific ways. Okay, so that you maintain the translation symmetry. Uh, so if you are putting it in a cube form, so where let's say we have A equal to B is equal to C, so there are three possibilities only. So one is called, this is just a primitive or a simple cubic. So this is a simple cubic structure. Then there is a body center, which is in a short form normally known as a BCC, body centered cubic. So what it means, like you have atoms or molecules in the corner of the cube and then one at the center. So this is a body center and you have atoms in the corner of the cube. So the another one is the face centered cube, so FCC in the short form. And then what you have is you have atoms on the faces of the cube. So here, for example, atom sitting here or on this face and on this face, and so 6 faces of the cube, and you have 6 atoms sitting on the faces. And of course, you have 8 atoms in the corner of the cube. So that is the basic cubic structure normally one uh, finds quite a lot. So particularly this, so for example, let's say BCC, so iron, for example, is a BCC. So the arrangement is in a BCC structure. So FCC are, so there are many, many of the metals are actually in FCC form as well. So you can have cobalt, then copper, okay, nickel, so these are many examples which are in FCC structure. For example, even sodium chloride. So maybe if you have gone through some solid state physics course, so NaCl is a typical example of FCC lattice. Okay, so then there is another type which we will also want to show here is a hexagonal lattice. So these are all, as you can see, these lattice, they are defined by their geometry. Okay, so this is a hexagonal arrangement of atoms. So again, you have uh, so this is A and B, and this is your C. Okay, so A, B, and C, and then what you have is you have certain angle here which is 120 degrees. So if you look at cube, so angle will be always 90 degree, of course, but in a hexagon, so the angle is different, and you have a elongation along the C axis or the Z axis. Okay, so this is another type of uh, lattice. So now you can see, so you have these different types of arrangement of atoms or different geometries. So how do we then distinguish these geometries? And these are basically what we are representing here. We are not representing the whole crystal, but we are only representing it through a unit cell. So all these are, you can call as unit cells. Okay, so these are all unit cells, and when you repeat these unit cells, you will basically get a 3-dimensional crystal. So how do we distinguish between these different unit cells, okay, or different lattice? So there are certain parameters normally we would use. So so when you look at these, so particularly the parameter, the first parameter you would say, what is the lattice? We call it a lattice parameter. What is lattice parameter? So that means what is the values of like A, B, C, So that is what represents the unit cell, and what is the angle between these axes. So normally, so if you see, look at this picture here. So what you have is you have A, B, and C, which defines the lattice parameter, and then you have angles alpha, beta, and gamma. So this is the first thing what you observe, and this is will give a distinction between different uh, unit cells or different lattice. So A, B, C, and the angles alpha, beta, and gamma. So if you take a cubic lattice, so for a cube, so A is equal to B, that is equal to C, and the alpha and beta and gamma, the angle would be all 90 degrees. That is quite straightforward. So if you take, for example, the hexagonal HCP lattice, so you have normally A will be equal to B and C will be different, okay? And then alpha, so the angle between B and C, which is your, so how we have defined, so B and C we say alpha, so B and C we say this is alpha, A and B is beta, and A and C is beta, and A and B we call gamma. So the gamma, so alpha and beta will be 90 degrees, but gamma will be 120 degrees. So this is how one parameter, if you can, so similarly for other lattice, these parameters will be different. So A, B, C can be different and the angles can be different. So this is one way you can distinguish between different lattice. So another thing is, the second one is known as a coordination number. So this is actually comes from like more important in chemistry when we talk about reactions and the chemical reactions. So coordination number, and in short it is normally represented by Cn. So coordination number means the number of atoms or nearest neighbor atoms. So number of nearest neighbors of an atom. So how many atoms are really the nearest to one of the atoms in the lattice? So that will define the coordination number. So which will be different for different lattice. Again, if you look at example, let's say take a BCC lattice. So the middle one here. So here in the BCC lattice, so if I take this point, this center point, which is a body center. So how many nearest neighbor it has? So it has eight, right? 1, 2, 3, 4, 5, 6, 7, 8. So these are the nearest neighbors or the coordination number in a BCC lattice. So similarly, if I take a FCC lattice, so here I have drawn that. So if you want to calculate the coordination number for FCC lattice, so this is a FCC lattice if you look carefully. So you have atoms in the corner and atoms on the faces of the cube. So if you look at one atom sitting on one of the face here, so you have how many atoms nearest neighbor? So 1, 2, 3, 4 in the corner, and then of course the nearest face, those sitting on these faces. So So let's say I can number it. So 1, 2, 3, 4. Maybe okay. So you have 1, 2, 3, 4, then 5, 6, 7, 8, and then you also have some neighbors in the adjacent cube as well. So you have then 9, 10, 11, 12. So therefore you will have 12, the coordination number will be 12 for any atom in FCC. So which is, in case of BCC it was 8, but in case of FCC it is 12. So that is how one can also, this is one parameter which will tell you that the lattice, they are different. So similarly you can also calculate for HCP and other forms as well. Okay, so this is one parameter. So another important parameter is, so probably you also know already, so known as packing fraction. That is known as atomic packing fraction. So that means what is this packing fraction? This is defined as volume of atoms in unit cell divided by the volume of the unit cell. Okay, so this is how you can calculate the packing fraction. So again, I have done an example here, or let's do an example here so it will be clear. So here it is, I have taken again the FCC lattice. So now if you look at a FCC lattice, so in fact, one thing which I forgot to mention here is, like, you can also calculate how many atoms are there in a unit cell. Okay, so if you look at these different structures, this lattice structure, so you can also calculate how many atoms are there per unit cell. So for example, if you look at this picture here, so a simple cube, so you will have one atom per unit cell. Do you know how it is a one atom per unit cell? Okay, fine. So basically what you have is, you have, so each atom sitting in the corner will be shared by 8 cubes. Okay, so that means they actually contribute 1/8 of their volume to one particular cube. So since there are 8 such atoms, so you have 8 into 1/8, so that will be equal to 1 atom per unit cell. So in case of BCC, it will be 2 atoms per unit cell, and in case of FCC it will be 4 atoms per unit cell. Okay, so now how do we then calculate this packing fraction in this case? So you have 4 atoms per unit cell. So to calculate the packing fraction, so what we say, we have 4 atoms, so number of atoms per unit, and so each atom, let's say, has a volume, has a radius r, so the volume will be 4/3 pi r cube. And since it is a cube, the volume of the unit cell will be, so if you say this is the length is a, the cube side is a, so the volume will be a cube. So this is what the packing fraction would be. But in order to calculate that, so we need to find out a relation between R and A, and that you can calculate. So if you look at this picture here, so what we do is, so this is, okay, so this is your R, this is your 2R, and this is your R, and the side is A. So and so this diagonal would be, the face diagonal would be square root of 2A. Okay, so this diagonal is actually, in terms of A, it will be square root of 2A, because it's a square again, and this is equal to 4R, and therefore R would be equal to, or A would be equal to, or rather I write R, so R would be equal to or A, I can write A will be equal to 4R by root 2, so which will be 2 root 2 R. Okay, so now if you substitute that, so you can calculate this or simplify this expression, and what you will get is 0.72, so something around that, 0.7 or 0.74 rather. So that means the packing fraction is 74%. So if you take a FCC lattice, this 74% of the cube is filled with atoms, and the rest is empty. So for BCC it will be 68%, and for simple cubic it will be 52%. So you can calculate this packing fraction using this formula, and by equating now what we are assuming is that the atoms, they are actually really touching each other very closely. Okay, so that is the assumption here. That is why we can say this is R, this is like this R2, R and R that we can make here. Okay, so this is how the packing fraction, and out of all these cubic and most of the all the lattice that you see in nature, so FCC has the highest packing fraction, so 74%. So similarly, hexagonal one also has the highest packing fraction, 74 as well. Any question so far, or is it fine? Okay, so you can do these calculations also for simple cubic and BCC structure as well. So let's look at now some examples of crystal structure, which are quite important when we talk about materials for particularly electronic material. So one example you, I think, already probably know is the diamond structure. So here what you have is the carbon atoms. So all are basically carbon atoms. The black one represents the lattice or the unit cell, and the red one, red lines represent the bond. So what you see is the blue ones, they form. So in the diamond structure, what happens is you have so the blue ones, actually, if you look at only the blue ones, so they form a FCC lattice. Okay, so the blue one forms a FCC lattice. So which is, let's say you say the origin at 0, 0, 0. And then the green ones, they also form a FCC lattice, but another FCC lattice with center at, it is the origin is replaced or shifted to 1 by 4, 1 by 4, 1 by 4 along the body diagonal axis. So the body diagonal axis is this one. Okay, so this is your body diagonal axis. So the other lattice, the green one, is shifted by 1/4 along the body diagonal. It will again make a FCC lattice actually. But then if you look at one unit cell here, so how many atoms you have is basically, so again for the blue one, you have 4 atoms, and all the green ones are inside the unit cell, so there are again 4 atoms. So that is, you basically have 8 atoms per unit cell. So this is your diamond structure. So which is like you will see a lot of this diamond structure in most of the semiconductor material. So silicon, for example, will be, of course, I mean, diamond is one example. So then you will have, yes, so what you are saying is you have the tetrahedral voids. So half of the tetrahedral voids are occupied by the carbon atoms. So silicon, germanium, so these are all assume or take this diamond crystal. So interestingly, carbon can also form another structure which is known as a graphite, right? So which is also quite well known. And there is a drastic difference between a diamond structure and a graphite structure. So graphite structure is nothing but it is a hexagonal, this is a hexagonal layer. This is hexagonal lattice. Sometimes it is known as a honeycomb lattice. And this is a layered structure. So it's a layered structure. So here the bond, this carbon-carbon bond is, in case of diamond is, so C-C bond is always the covalent bond. However, in graphite, what you have is in the plane, so these blue ones or the green ones, in between them, the bonding is still, it is a carbon-carbon covalent bond. However, there is a very weak bonding from one layer to another layer. So if you look at the bonding from this green to the blue one, or this layer to this layer, so the bonding is very weak, which is something like, you know, already van der Waals bonding. So it is a very weak bonding, and this gives this layered structure to graphite. And you see, in both cases you have carbon as the basis. Okay, it is the atom, carbon atom, but they are arranged in different crystal structure, and that leads to very different properties of these two materials. So for example, diamond is, so if you compare, so diamond is, it is hard, one of the hardest material. It is insulator, okay, although it has a good thermal conductivity, but graphite, on the other hand, is brittle and also conducting. So the same carbon atom you have, but depending on how they are arranged, depending on the crystal structure, so the properties are very different. Sometimes these, so carbon can also have, when you go to a nanostructure form, so if you have time, we will also look at that. So in the, if you reduce the size of carbon, I mean these structures, so in a nano form, so carbon can have some other different arrangement as well. So you will have different structure. So in nano structure form, so I just mention it here. So you can have something known as a fullerene. So it is a consists of C60 carbon atoms, unit cell, fullerene. Then you can have carbon nanotubes. So it is again a form of carbon nanotube, like a hollow tube where carbon atoms are arranged in a hexagonal pattern. And then you probably also heard of a graphene. So it is like a 2D material. So graphene is nothing but just if you take one layer from graphite, so that is basically your graphene. So it is possible to actually just take remove one layer and it is still stable, and that is a two-dimensional material, uh, and normally you will observe it when you go to the nanostructure. So graphene is like a the building block of graphite. Okay, so if you put many graphene layers, so you get a graphite. So the same atom, so when you change and then of course, if you look at their properties, so the electrical properties or their mechanical properties, they are also different. Okay. So another interesting crystal structure is, from the semiconductor point of view, is there are two basically the same. So here the name comes from zinc sulfide. So zinc and the two atoms, zinc and sulfur. So here earlier what you see is they are all similar. Okay, so all carbon or silicon. So one type of atom, but a crystal can be made of two different atoms. So let's example, this is the earliest known crystal structure, the zinc blende and wurtzite structure. So many semiconductors, they follow this kind of structure as well. So what is a zinc blende structure? So now, which one? Let's say this green one is a zinc, and the blue one is the sulfur. So what you see, the green one, they make again a FCC lattice, okay? And the sulfur again sits at the tetrahedral voids. So sometimes people also represent it in the other way. So you can say this green one is a sulfur one, and then the zinc would be sitting in the tetrahedral voids within the lattice. And so this is a zinc blende structure. It is a FCC structure. So very similar to the carbon one, but now instead of only one type of atom, you have two different type of atom, zinc and sulfur. So that's why it's a zinc blende structure. So examples are, so gallium arsenide. So all these are really famous semiconductor materials. Gallium arsenide, then indium phosphide, gallium nitride. So these are these compound semiconductors, which are the atoms are arranged in this zinc blende structure. So the zinc sulfide can also have a hexagonal structure, so it can be a HCP structure as well, but it is not observed that often. So if you talk about semiconductors, mostly they will be in this zinc blende structure. Okay, so this is the most common form of structure you will encounter for most of the compound semiconductors. But you can also have a HCP structure, where again you have, this is your zinc and this is your sulfur. So again you have the same, instead of the FCC lattice, so the zinc is forming a hexagonal lattice. So that is your wurtzite structure. Okay, but many of the semiconductors actually they follow this zinc blende structure. Okay, so many oxides also, so these are compounds, or there is zinc oxide, for example. Okay, so this is also as a zinc blende structure. Okay, so these are some structures which are important that you know, that when we go further, so that you know what is the crystal structure of these semiconductor materials. And when we discuss in detail of some of the materials, we will also again see what is the structure here. So if I say, for example, here gallium arsenide, so gallium arsenide would exactly look like the same. So instead of, let's say, zinc, I will have here gallium, and instead of this sulfur, I will have arsenic. Okay, so otherwise the structure would look exactly the same. Uh, yes, you can call it as a octahedral voids in the HCP, but in octahedral voids can also, you can also have it in FCC lattice as well. So the voids you can, so you can have both kind of voids in the cubic or the HCP lattice. Okay, so both type can exist. So for example,
So
if
and
you
in
take,
wurtzite,
sorry,
sulfite is in the octahedral voids.
no, in tetrahedral. This is again very similar to carbon. So this is in the tetrahedral void. No, the question is, I think Anirudh is asking in HCP, it is an octahedral void. So not necessarily. So if you look at this, for example, here, so this is octahedral, but this one, so this is a tetrahedral void. Okay, so this atom where it is sitting is a tetrahedral one, but this one is a octahedral void. Okay, so both are possible, but in what I am saying is in FCC lattice also you can have atoms sitting in octahedral voids as well. Okay, so you can, so one example is like iron oxide. Okay, so iron oxide is one example where you have atoms, iron, they can go to octahedral as well as tetrahedral side. However, the iron oxide is actually FCC lattice. Okay, so it is not HCP. So all the crystals, all these lattice can have octahedral voids as well as tetrahedral voids. Okay, so uh, so one interesting thing that happens with crystals, so what we talked about most of these regular arrangements, but what can happen is you can have actually defects in the crystal. Okay, so if you look at a perfect crystal, so you have atoms which are arranged like all the lattice sites are occupied by atoms, but it can happen that due to, but you know these atoms are not idle. Okay, so they are not just sitting there like that, so they are actually vibrating, right? So these atoms have, they are vibrating atoms, which is due to the this is a thermal vibration that you have. Okay, so they are almost like a, one can assume it's like a simple harmonic oscillator, so which oscillates with their mean position, which is the lattice point. So they are vibrating around that, and that is due to the temperature. Okay, and it can happen that at certain temperature, even like if you increase above, let's say, 0 Kelvin, so what it could happen that some atoms, most likely maybe the surface atoms in this case, so they have enough thermal energy and they will be free from their lattice side and they will go and sit somewhere else. So for example here, so this atom has jumped and is sitting on the surface uh, somewhere on the other on two of the other atoms on the surface, and that is how you can create a defect which is known as a vacancy. So you can create a defect due to this thermal vibration, and for some, so this is again a probabilistic thing, and these are normally known as also a thermodynamic defect. And as you can see here, so you shift the atom to somewhere else and you create a vacancy. And this vacancy, so what could happen, like another atom from inside the material, so it can move to this vacant position, and then this, so when it moves to this vacant position, so here in this picture you see, so now this vacancy is occupied by an atom, and the vacancy has actually moved to inside of the material. So it has diffused inside the material. So you can have a diffusion of vacancy inside a material. I think now it's almost time. So we will continue with this discussion tomorrow, and then we will look at, since we don't have enough time, so I couldn't discuss about this grain and difference between grain and grain boundaries. So we will, so once we have an idea about this vacancy and thing, so then I can tell you what is the grain and polycrystalline material. And then also we will look at the electrical properties of the material, how that one can use that to find the difference or classify different materials. Okay, any question? Okay, so if there is no question, so we can stop. Yeah, thank you then. So we will then meet on Monday.